The sums of infinite series. The sum of an infinite series is very closely connected to the limit of an infinite sequence. For the geometric sequence below, find the partial sum equation Sn and evaluate the limit. All right, we're going to need to evaluate a limit because this is an infinite series. Okay, but what we're going to start with are just partial sums. For example, the very first sum, we could call maybe like S1 would be the sum of the first term. Well, the sum of the first term is literally the first term, which is 1/2. S2, the sum of the first two terms, would be 1/2 plus 1/4, which is going to be equal to 3/4. For S3 would be 1/2 plus 1/4 plus 1/8. 1/2 plus 1/4 is 3/4. 3/4 is the same thing as 6/8. So 6/8 plus 1/8 would give you 7/8. All right, so if you look at just the first three here, you can almost start to create a pattern in what we see. You've got 1/2, 3/4, and 7/8. As you move along, the denominators are doubling, okay? So the next denominator, of course, will be 16. But if you look at the numerators that we have, the numerator is always one less than the denominator. You got 1, then 2, you got 3, then 4, you got 7, then 8. We can expect for the fourth, it's going to be 15/16. It's going to be 15/16. So if you think about the individual fractions as you're moving along through the sequence, with that numerator always being 1 away from the denominator and the numbers themselves being larger, we're actually getting very, very close to one whole. It appears every time you add another term on, when you're adding that little bit more, you're getting closer to one whole. Next, what we want to do is find the partial sum equation of Sn, an equation that would allow us to find the sum of the series with n number of terms so that we don't have to continuously add on to these. And recall that this is a geometric series. Since we have a geometric series, we can use this formula to figure out the sum of n terms. Okay, you need your first term, you multiply that by 1 minus r to the nth power divided by 1 minus r. Okay, so for our particular problem, t1 is 1/2. That was our first term. We then have 1 minus r. Our r value here, the factor that we use to go from 1/2 to 1/4, 1/4 to 1/8, 1/8 to 1/16 is going to be 1/2 as well. So it'll be 1/2 to the nth power divided by 1 minus 1/2. Okay, and with a little bit of algebra to clean this up, the bottom you're going to notice is actually just 1/2. You have 1 minus 1/2, so you get back 1/2. Whoops, that n is going to be on the inside. Okay, so you have a factor of 1/2 on the top and a factor of 1/2 on the bottom. Those can cancel with each other, which will give us 1 minus 1/2 to the nth power. And we can actually use that to find any sum that we want. So if we wanted to find this sum here, S3, we could just plug a 3 in for that exponent, and it will give us 7/8. Okay, so I'm going to take 1 and subtract. For the 1/2, I'll just type it in as 0.5. Raise that to the third power. I get that as a decimal, but if I convert it over, we see that we get 7/8. All right, so we have an equation that can generate the sum of any number of terms that we want. But what we've really got here is an infinite series. We want to know what would this add up to if we kept adding on more and more terms. Right, we start with the 1/2, then we had 3/4, we had 7/8, we get 15/16, and so on. But what would we get to if we continue this on forever? And to do that, we're going to evaluate this as a limit. We're going to take the limit as n approaches infinity of this expression and see what that would equal. And the way that we're going to approach this is we're going to imagine putting in a really large number for n. So if we take 1/2, which is a value less than 1, and we continue to raise it to higher and higher powers, every time 1/2 is multiplied by itself, you get back a little bit less each time. Each time you get a little bit less. So when n is a really big number, this 1/2 essentially becomes 0. half of half of half of half of half of half, and so on, will eventually shrink down to almost zero. Almost. Does not actually become zero, but gets very, very close. So if we can think of that as zero, we've got 1 minus 0, which means that our limit will be 1. The limit of the simplified Sn as n increases is 1. We can say that the sum of the infinite series, 1/2 to the nth power, is 1. If the sequence of partial sums has a finite limit, like the example that we just looked at, then the infinite series is said to converge at that sum. It's said to converge at that sum. You actually get an answer out of it other than infinity. All right, so when does that actually happen? 1, we need a geometric series. And 2, we need a very particular R value. We need an R value whose absolute value is less than 1. Okay, so if the absolute value of R is less than 1, then the infinite geometric series converges to a sum that would be calculated using this. That sum will be T1 divided by 1 minus R, which is a really nice compact equation for something that might sound really technical like an infinite series. Okay, so let's prove that that's actually true. And the proof is actually relatively easy and not much different than what you saw me do in the last example. So let's prove that this is true. We're going to be working under the assumption that the absolute value of R is less than 1. So it could be 1/2 or negative 1/2. It could be 1/3 or negative 1/3. It could be 2/3 or negative 2/3. The absolute value would be less than 1. The nth partial sum of a geometric series is calculated using this, as we've seen before. So if we take the limit of that as n approaches infinity, it will simplify down to this. All right, so let's look at all the parts that we have here. We don't really know the value of R, but it happens to be less than 1. So if you continue to raise a number that's less than 1 to a power, you get back less every time. You keep getting back less until this basically becomes a 0. So for the top part, when we begin to evaluate as n goes to infinity, the top part is going to look like T1 times 1 minus 0. Now for the bottom, the R isn't getting raised to a power, and we don't know what the R is, so we have to leave that in this. We have to leave in the 1 minus R. But look what happens on the top. You have 1 minus 0, which is really just 1. So if this is 1, and you multiply that by T1, you get T1, and there's your denominator, 1 minus R, which is this. And that's how you can calculate the sum of an infinite geometric series if the absolute value of R is less than 1. So what happens when the absolute value of R is not less than 1? What if it's equal to 1? What if R is 1? Or if the absolute value of R is greater than 1? What happens in that case? Well, if that occurs, then the sequence of partial sums will approach infinity, or it just won't have a finite limit. Okay? And in those cases, we'll describe them as diverging. They will diverge. So if it actually goes to a value, and that would be when the absolute value of R is less than 1, then we say that it converges. If it doesn't do that, then it will diverge. Now, it can diverge for a couple of different reasons, and it really just depends on what we see in those R values. So we're going to look at a couple different cases here. All right, first case. If the absolute value of R is greater than 1, then R to the nth power increases or decreases without bound as n increases. Okay, so if R is a number like 2, and you keep raising 2 to bigger and bigger powers, it just continues to increase forever. If R happens to be a value like negative 2, and you're raising it to a power, it continues to get larger and larger as well. Of course, it's going to flip-flop between positives and negatives depending on your exponent. If it's an odd exponent, it's going to be a negative number. If it's an even, it's going to be a positive number. But it's still going to keep getting bigger and bigger. It's going to get bigger up in a positive direction, then bigger down in a negative direction, then bigger up, and so on. So regardless of the direction that it's going and the fact that it's moving back and forth, it's continuing to get bigger and bigger and bigger. Thus, Sn becomes infinite and the series diverges. Well, let's actually write the word. Becomes infinite. Because it's not infinity, it's infinite. Thus, Sn becomes infinite and the series diverges. Okay, other cases. What if r is equal to 1 versus negative 1? What if r is equal to 1? Then the series becomes divergent as well. Because when you have a 1 in for r and you're raising it to powers higher and higher and higher, you're always getting back 1. Your term is never changing. Whatever t1 was, and when you multiply it by 1, you still get back t1. And then when you multiply by 1, you get another t1 and another t1 and another t1. Okay, and you might see this as, okay, it's constantly the same value. But if you keep adding the same value over and over and over and over again, it will go to infinity. If t1 happens to be a negative number, it's going to go to negative infinity because you're just continuing to add on the same amount over and over again. All right, now here's the weird one. When r is negative 1, the series is divergent. And here's what it's going to look like. Your very first term is going to be t1. Your second term is actually going to turn out to be negative t1. So when you add that term on, you create a 0. And then after that, you're going to get a regular t1, which is going to give you t1 as a total. But then your next term is going to be negative t1, which will create a 0. So you're going to constantly be flip-flopping between having t1 and 0, which makes it divergent. For example 1, we're going to find the sum of the infinite geometric series 9 minus 6 plus 4 minus so on. Okay, so this is a geometric series, which means that it comes from a geometric sequence. That means that there's an r value that exists. The r value can be found by taking consecutive terms like negative 6 and dividing it by the term before it, divided by 9, which will reduce down to negative 2/3. And that will hold true for the next two consecutive terms. If you take 4 and divide it by negative 6, you also get negative 2/3. So that is our r value. In this series, the r is negative 2/3. And t1, of course, is 9. Will be the value that we start with. So if I were to continue this series forever and keep adding the terms, I would have 9 minus 6 plus 4 minus the next number plus the next number. It will converge to a certain value because the r value's absolute value is less than 1. And to figure out what that is, I can use this little formula, t1 divided by 1 minus r. That's all I have to do to figure out what this will converge to. So t1 is 9, and we're going to have 1 minus negative 2/3, which will become adding, right? So you got 9 over 1 plus 2/3. That would be the same thing as 9 over 5/3. And with some keep change flip, we've got 9 over 1 multiplied by 3/5, and that would give us 27/5. If you continue that sequence out forever, it will become 27/5, or as a decimal, 27 divided by 5 would be 5.4. So you could answer that way as well. All right, for example 2, for what values of x does the following infinite series converge? All right, well, first off, if this infinite series is going to converge, it will need to be a geometric series, which means that there would need to be an r value. So let's see if we do have an r value. What would we multiply 1 by to get x minus 2? Well, of course, that would be x minus 2. So we should be thinking that our r value has to be x minus 2. And that does hold true as you go from term to term, because we're just going to raise x minus 2 to the next highest power as you go along. So that is our r value. It's x minus 2. And if this is going to converge, then the absolute value of the r value, x minus 2, the absolute value of x minus 2 must be less than 1. Now, you may or may not recall from Algebra 2, if you have an absolute value set less than a number, you can actually drop those bars, just write it as x minus 2, and show it as less than 1, and greater than the opposite of that number, which is negative 1. And now we can solve for a range of values of x by simply adding 2 to everything. So negative 1 plus 2 will give you 1. It would cancel there. and 1 plus 2 will give you 3. Okay, so any value greater than 1 and less than 3 could be plugged in for the x, and this will converge. It will converge to some value. For example 3, we're going to look at a neat observation for fractions whose decimal form is an infinite repeating decimal. For example, 5 over 11. Okay, 5 over 11 is a repetitive 0.45454545 forever. Okay, and in some cases, you run into these. Maybe you do a calculation, you don't know what the fraction is that it comes from, but you run into these repetitive decimals, and you would like to be able to change it into a fraction. Now, most calculators can do that for you, but as a neat observation, we can show you that you can convert this into a fraction, thinking of this as an infinite geometric series. Okay, the first step to it is to actually just break up the repetition. So you can write the repeating decimal in its small parts here. So you got 0.45, you've got 0.0045, you got 0.000045. And of course, if you add all these together, the 4 5s are just gonna kind of fill in the spots for the other zeros, and you would get back to this repetitive thing here. And of course, it does go on forever, right? So plus dot, 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 and you can keep this process up here. So the neat thing here is that there really is an R value that you can multiply each term by to get the next one, okay? Because all that's really happening in the multiplication here from 0.45 to 0.0045 is that the decimal has moved 2 spots forward. Then from here, 2 spots forward gives you that. So what number do we multiply by to move the decimal 2 spots forward? Well, you may actually think of it as dividing. If you divide by 100, it's going to move that decimal forward 2 spots. Now, instead of thinking of it as dividing by 100, because that might not work well for our infinite geometric series, we'll just think of this as multiplying by 0.01. Multiply by 100th. If you multiply by 1/100th, you get the same thing as if you were to divide by 100. So that's going to be our R value. R is 0.01. Our T value will be the one that we start with here, 0.45. Okay, now let's take our little equation, T1 over 1 minus R. T1 will be that number, right? 0.45. Divide that by 1 minus 0.01. That can be simplified as 0.99. So we're going to get 0.45 over 0.99. In which case, because we're now just looking at a fraction, we can go ahead and multiply the top and the bottom by 100. We could rewrite that simply as 45 over 99. These are equivalent fractions now. You can then reduce by the common factor they have, which is a 9. If you divide by 9, top and bottom, you're going to get 5/11ths, which is the same thing that we start with there. So again, we constantly run into these repeating decimal answers when we do calculations. Most calculators can just convert it into the 5/11. They can do that. But as a neat observation, we can relate this to an infinite geometric series and show that this formula can also get us to that spot.
Wait, what?